So in this video, I'm going to be talking about how to make a full adder from half adders, as well as making a 3-bit parallel adder and subtractor using multiple full adders. First, we're going to be talking about the basics of a half adder. A complete full adder consists of two inputs, A and B, and two outputs, the Cout, which is also called the carry, as well as the sum. The inputs go through the XOR gate and the AND gate, just like in the diagram currently showing, making a simple binary adder. For example, 1 plus 0 or 0 plus 1 will be equal to 0, 1, while 1 plus 1 will be equal to 1, 0, as shown in the order by the LEDs. To verify it, let's make it into a real circuit on a breadboard, just like what I'm showing you right now. So this is what happened when you flip the switches like just now. As you can see, they have the exact same output. Now we can make it into a full adder. To do that, we can add an OR gate or a third input Z, then connect the wires as shown, making one additional input that can be used to perform the binary addition. This is very important for combining multiple full adders together later on. For now, it's the exact same thing with half adders but with an extra input. So basically, we'll have one input of 1 equals to 0, 1. Two ones will become 1, 0, just like the previous half adder. And now, three ones will become 1, 1. We can also make it into a hardware based on the simulation to get the same output. Now, we can make it into the 3-bit parallel adders. We can combine three full adders by connecting the previous carry output into the next carry input full adder. The first carry input will be connected to the ground to represent 0, and the third carry output and the sums will be connected to the LEDs as shown in the simulation. Whenever there's a total sum of over 1, another input of 1 will be carried from the previous C out into the next C in, making a simple calculator that can add two sets of 3-bit binary numbers represented by AAA plus BBB. Unfortunately, when the output binary number requires 4 figures, an overflow will occur, which is shown in the LED change in the final carry output LED that is ignored. This will make the final 3-bit answer invalid, so it isn't really that functional. Anyways, here are some few output examples, which is just basic additions of two sets of 3-bit binary number. Once again, we can make it into the hardware using multiple IC chips instead to get the same output. Finally, we can make a 3-bit parallel subtractor. Before that, we must know about the 2's complement. In real life, there is no gates that allow subtraction, only OR gates exist. Thus, we must perform the first complement to invert each of the set B numbers, then add 1 to it, which is the second complement. We can do this by using NOT gates to invert it and add 1 through the first carry in of the full adders. This way, the positivity and negativity of the numbers of set B will be inverted to perform addition instead of subtraction. For the output, besides overflowing, subtraction can sometimes cause negative numbers too, in which this case, a fourth bit is required to represent a sign bit so that the negative numbers can be shown. But for now, negative numbers that are over 3 bits are invalid. But basic subtraction can still occur as we can see from the output right now. We'll do the same thing with the 3-bit adder hardware by adding a NOT gate IC chip and add 1 through Cin. As you can see right now, they also have the same exact output. And that's about it. Thanks for watching.